Hello, welcome to Fundamentals of Acoustics. Today is the 5th day of this particular week, and today and tomorrow we will discuss propagation of one-dimensional waves in a spherical reference frame. So, we will go back to the topic which we were discussing earlier, and specifically today we will introduce a concept called volume velocity. So, this particular concept becomes very handy and useful in our attempts to compute, because typically what happens is, suppose there is a pulsating surface or for that sake a loudspeaker, and if it is emitting sound, then we do not necessarily know how much pressure is being generated just at the diaphragm. But through laser measurements or some other techniques, we can measure the motion of diaphragm, and we also know the area of diaphragm which is moving. So, we know that how much air it is displacing each second. So, that is essentially known as volume velocity, and we will see and we will develop it mathematically, and that is the concept we are going to develop today. So, last week we had developed equations for one-dimensional spherical waves, and we had said that pressure was real portion of P plus over R E minus j omega R over C times E j omega t, and velocity for 1D waves in the spherical frame of reference is real of P plus over R E minus j omega R over C E j omega t, and then of course divided by specific acoustic impedance, which is Z. And we had actually calculated Z, and we found that Z was a function of R and omega, and the relationship for Z was 1 divided by 1 over j omega rho naught R plus 1 over rho naught C. So, this is what we had developed last week, and now we will develop it further and introduce this notion of volume velocity. Consider a sphere, okay, and let us say that it is a sphere of a radius r naught, and what this sphere is doing is that it is emitting sound, and it is expanding and contracting, and it is uniformly expanding and it is uniformly contracting. So, it is emitting sound, and we are interested to find out its volume velocity. So, this is A, this is B, this is equation C. So, from A and B we know that the complex amplitude of pressure is P plus over R E minus j omega R over C, and complex amplitude of velocity is P plus over R z E minus j omega R over C. The complex amplitude, and because both these waves for pressure as well as velocity, they do not have a reflected component, there is no P negative, right, because in our assumptions we had said that there is no reflected wave. So, this P r over r time P, which is a function of r and omega, complex pressure amplitude, it corresponds to amplitude only of the outward moving wave. So, I will also put a positive on these expressions. So, from here I can say that u plus r omega equals p plus divided by r e minus j omega r over c, and times 1 over z, and 1 over and z is 1 divided by this entire expression. So, 1 over z is 1 over j omega r rho naught plus 1 over rho naught c. Okay. Now, we go back to this sphere, pulsating sphere. If we are interested in pressure field and velocity field at the surface of the sphere, then the value of r at the surface of the sphere is r naught at the surface of the spheres, right. So, at the surface of a sphere, r is equal to r naught. So, u plus, so the velocity on the surface of the sphere is u plus, which is a function of r naught and omega, and that equals p plus, which is a constant, divided by r naught e minus j omega r naught divided by c times 1 over j omega r naught rho naught plus 1 over rho naught c. Okay. So, what we do here is now, so I can rewrite it as p plus divided by r naught e minus j omega r naught over c times, and I will add these terms j omega rho naught r naught c, and what I get here is c plus j omega r naught. Okay. So, from this I can express p plus as, so I am going to just cross multiply. So, I will get u plus, which is the complex velocity amplitude, times r naught e j omega r naught over c. So, exponent of minus j omega r naught over c, when it goes to the positive or the other side, it becomes a positive thing, times j omega rho naught r naught c divided by c plus j omega r naught. So, now what I do is I take this r naught out of the bracket and I multiply this with the other r naught. So, this is equal to u plus r naught omega, which is the velocity of the diaphragm or the sphere, times r naught square exponent j omega r naught over c times j omega rho naught c divided by c plus j omega r naught. The other thing I do is I divide the numerator and denominator by c. So, what I end up with is this c goes away and this c goes away and it gets replaced by 1, and here I have in the denominator c. Okay. Now, we define volume velocity of the source. So, the point is that suppose this is the source of the sound, this pulsating sphere is the source of the sound, then volume velocity of the source, what is it? It is the dot product of velocity times the surface area. What does this mean, the dot product? It means that suppose this is the surface area, then the surface area at each point has a normal, right. So, that is the normal, and u may be in this direction, but what we are really interested in computing is u which is aligned to the normal, which is its component. So, that is what it means. So, this is velocity, this is complex velocity times normal area. Okay. So, if the pulsating sphere is just moving in and out uniformly, if it is, then the u and its surface area are mutually normal anyway. So, this dot product will be, so mathematically this is u modulus of a times mod of a modulus of u times mod of a times cosine of theta, and cosine of theta, if it is uniformly expanding and contracting, that will be 1. So, in that case it will be u times 4 pi r naught square, right, and this is the complex velocity. Complex velocity. So, what does this show? So VVS, so VVS will have 4 pi r naught square times complex velocity amplitude times E j omega t, right, that is what how it is going to behave. Now, this term looks very close to this term, except that in this term, in the red term, there is no 4 pi. So, what we can write it as, so I can, so let us call this equation A and let us call this equation B, and I say that comparing, and this VVS, I am sorry, I should express it as that. So, VVS, if I compare B and A, comparing B and A, we can write that P plus equals complex velocity amplitude divided by 4 pi, because this is 4 pi r naught square times u r naught omega. So, this is complex velocity amplitude times E j omega r naught over c into j omega rho naught divided by 1 plus j omega r naught divided by c. Okay. Now, we make a simplification. If omega r naught over c is very small compared to 1, what are we doing? We are looking at these two terms and we are saying that omega r naught c is very small compared to 1, that is r naught is extremely small compared to c over omega, which means r naught is very small compared to c is frequency times lambda and omega is 2 pi frequency. So, r naught is very small compared to lambda over 2 pi. So, if r naught is very small compared to lambda over 2 pi, then this term it approximates to 1. So, in such a case P plus equals complex amplitude of volume velocity divided by 4 pi E j omega r naught over c times j omega rho naught. So, if I know the velocity of a pulsating sphere and I know its radius, I can compute its volume velocity, and from that I can calculate the value of P plus. Once I know the value of P plus, I can say that actual pressure is what? Real of P plus E minus j omega r over c E j omega t. Okay. So, this we go back to the original relation, we are going back to this relation. Okay. So, whatever we have done, we have calculated P plus in terms of volume velocity, and we are plugging that relation back into the expression for pressure. So, with that goal, I can write that pressure is real of volume velocity complex amplitude divided by 4 pi E j omega r naught over c times j omega rho naught. So, that is my expression for P plus. So, this is VVS over 4 pi e to the power of j omega r naught over c times j omega rho naught times, so that is P plus over r times E minus j omega r over c E j omega t. But we have said that omega r naught over c is very small compared to 1, and that will happen when r naught is extremely small compared to lambda over 2 pi. Now, because of this assumption, we had made one simplification which was here, but we could have made one more simplification, that when omega r naught over c is very small, then this entire term, this also approximates to 1. So, in that case, this term, this approximates to 1. So, for the condition when omega r naught over c is extremely small, we can write that pressure equals real of VVS over 4 pi j omega rho naught E minus j omega r over c E j omega t. Okay. So, this is our expression for pressure in terms of volume velocity. So, that concludes the discussion for today on volume velocity, and tomorrow we will extend this discussion, and then we will actually apply some of these concepts to find out what happens if there are two point sources close to each other and they are emitting sound, then how does the overall sound pattern far away from those two sound sources looks like. So, with that I close for today, and we will meet once again tomorrow. Thank you.